A reminder that this talk is tomorrow from 4 to 5. You all should have received this handout in an email. This will be playing in the Enrichment Center if you want to sit there and talk with other people about it. If not, feel free to join the Zoom link. Unfortunately, I will be in the middle of a schedule meeting, so I won't be able to be there. Otherwise, I would absolutely love to find out what this is about, because this is something that's a step up from the part of graph theory we would cover. But there are games that are built on graphs like this. Searching for a fugitive triangulated capture. If you are on one of these vertices, where can you be? Where can you be seen? Where can you not be seen? There's a lot going on here. I think this is worth going to. You should take a look at it. Tomorrow, 4 o'clock. I want to talk today about the minimum spanning tree problem. There's a terminology here that needs to be defined. Suppose we have a connected graph with cycles. Then I can start removing edges. Somebody tell me why that sentence is true. If I were to take an edge away and disconnect my graph, then that edge would be a bridge. And no bridges can be parts of cycles. There's got to be another way to get from vertex A to vertex B on the other part of the cycle if I remove that one edge. So let's continue this process. The new question is now, is this graph a graph that contains cycles? If it is, take an edge from a cycle, throw it out. Eventually, what has to happen? So I run out of, not edges, but I run out of cycles to pull stuff from. But at every point in this process, we were connected, right? So now I have a connected graph with no cycles. What kind of graph do I have? Tree. Now, it's not just any tree. This tree has the same set of vertices as the original graph. And it's still connected. We touch all the same places. We don't have any cycles. We stay connected. We still span the same set of vertices. I'm going to call this a spanning tree. Technically, I should define it this way. A spanning subgraph of G is a proper subgraph so it has fewer edges, but has the same vertex set. And if this happens to be a tree, then we have a spanning tree. Now there's another way to build a spanning tree. Another way to build a spanning tree, instead of thinking of taking edges away, we can think of putting edges in. So I could say, let's start with the empty version of G. Take away all the edges. Now put one in. Put another one in. When you start to put your third one in, you can then say, hey, did I make a cycle? And if the answer is no, put another one in. And if the answer is still no, put another one in. At some point, you'll have hit n-1 edges. Where the order of my graph is n, that'll be a spanning tree. So I can do this in two different ways. I can do it by subtracting, or I can do it by adding. And the way in which we choose to do this can define how we get the spanning tree out. Every graph must have a spanning tree, as long as that graph is connected in the first place. Otherwise, you could get a spanning forest, but that just means you build multiple trees. So let's work on one tree. Questions? So how do we decide which edges we want? Well, that depends on a lot of factors. If you just have any graph, then you can make a lot of different spanning trees, right? But some edges will be preferable to others. Why? I don't know. That depends on what your graph represents. So let's assign to each edge a weight or cost. That's just going to be a number. W of E, where E is the edge and W of E is its weight. This is a function. Then I can define the weight of my subgraph. The weight of H is the sum over all the edges in the edge set of H of the weight of the edge. So now I can say this will be my order of preference. I want the lowest cost or the lowest weight. And if I can find one, that's called a minimum spanking tree. First question for you. Why must the graph with the lowest, the subgraph with the lowest cost be a tree? Right, because if I want to get from A to B and there's a cycle, I can just pull one edge out and go the long way around the cycle. That would lower the total cost. It might not lower the cost to go from A to B, but it lowers the total cost. That's my goal, is to lower the total weight or cost. So we have to have a tree associated with this minimum. So the question is, how? There are two most commonly used algorithms to do this: Kruskal's algorithm and Prim's algorithm. Neither of them are particularly short. Both of them are greedy algorithms. What's that mean? Chapter 3, section 1 and 2 of the discrete text. The internet is your friend. What's a greedy algorithm? Ben?
It's a method of solving a problem where you take the best option for each step and not the overall best option.
I don't look any further than the very next step, and I take the best thing I can do then. The algorithm we did in discrete was making change, right? Here's a number of coin. I want change from my dollar purchase. You get 27 cents. What's the fewest number of coins you're going to get? Take the biggest possible coin out of your pile first. That's the greedy part. Take the biggest first thing you can do, or the best, for whatever my definition of best is. And that's dependent on the algorithm. But in this case, my goal is to take a minimum spanning tree. So my definition of best is going to be cheap. What's the lowest weight or lowest cost? I need a graph to start with. We're going to use this one. You should copy it down. I'm not doing the one in the book on purpose. That one's already done. Let me do a different one so you can see it in multiple places. What I need you to do for me first is to create a sorted list of the edges, sorted by weight. Ruskell. Now, what I did is I went through and I made a list of edges alphabetically. AB, AD. I already did AB, so I can do BC, BD, BE. I built that list that way. And then I sorted them, smallest to largest. First thing I do is I run into a problem. What's the problem you see right away? There are two edges of weight 5. How do you want to break ties? Here's the advantage. I don't care how you choose to break ties. Literally, it's a coin flip. You could have a deterministic method. I will always take the edge with the first letter in the alphabet that shows. Or I could always take the one with the last letter in the alphabet that shows. Your call. It doesn't matter. You need, for your implementation, a tiebreaker method. It could be completely random. Your call. Now again, I'm a geek. I did these alphabetically, and I did them tiebreakers alphabetically. So this is my ordering. Yeah. What do I want to start with? If my goal is to find a minimum spanning tree, I should start with the smallest one. But all that means is you're going to work from the bottom of your list to the top rather than from the top to the bottom. That's fine. This is the advantage of sort algorithms. Okay, switch, sort descending to ascending instead. All right, here's the deal. Instead of pulling edges off, I'm going to put edges on. Kruskal's algorithm builds the graph from smallest edge to largest edge, adding until we hit n-1 edges without having built a cycle. Which means I'm going to start with an empty set of vertices. Drat. I knew I made it too big. It doesn't quite fit on one page at the same time. We'll zoom out. There. Now I can see my list and I can see my empty set of edges. Here's the deal. Formally, I would keep several counters and several trackers all running together. As long as the total number of edges I have added is less than what? Well, what's n? So I need 6. As long as I have not added 6 edges yet, keep going. While total edges less than 6, less than or equal to 6, do. My starting weight is a 0. Add your lowest edge. Write down your total weight. Write down your new number of edges. Have we reached 6 yet? Did I make a cycle? 1 edge. I couldn't make a cycle. Add your next lowest edge. My total weight is now 10. I have 2 edges. Haven't reached 6 yet. Keep going. Have I made a cycle? Onward. Third edge in the list. Is DF. My total weight is 16. Did I make a cycle by adding this edge? I probably should check that first, because if I make a cycle, I don't want to add that edge, right? I need to redo the order in which I'm doing this. What is my next edge to add? AB. Because I didn't make a cycle, I can do that. Total weight is now 23. Next edge, BE. If I add it, will I make a cycle? Then add it. Total weight, 30. 1, 2, 3, 4, 5. I'm getting closer. The next edge in my list is BC. Add it? Why not? If I add BC, I'll make a cycle. How about EF? Same problem, I'll make a cycle. BD. There'll be a cycle. EG. Yay, I can do that one. That's edge number 6, stop. Total weight. Now, I want you to understand that I am by no means saying this is necessarily fast. I mean, this was a small graph with 7 vertices and what, 3, 6, 9, 12 edges. Even the single graph here with 20 vertices and way more edges, this would take a while, wouldn't it? And if I ask you to run Kruskal's algorithm, showing me the output is not the correct answer. What the hell do you mean it's not the correct? Well, technically, you should, at each and every step, keep track of everything you've done. And, oh no, I couldn't add that, I couldn't add that, I couldn't add that. Here we go. Bah, that's nasty. But it works, yes? Questions? Given the fact that I have 3 different edges of weight 1, 2 different edges of weight 2, 3 and 2 different edges of weight 4, and an edge of weight 5, there are lots of different possible minimum spanning trees here. And it depends on your choice of tiebreaker. You can get at most 2 of those 3 edges of weight 1. Why? If I add all 3, I get a cycle. And then, depending on which ones you've used, you could get either of the edge 2 weights, right? If you use AB and BE or AE and BE, you're going to have both B and E at some point, yes? So you can either use BC or EC, again, depending on your tiebreaker. What edge can you guarantee me will never get used in any minimum spanning tree? Because the highest possible weighted edge. I guarantee you we're not going to use that in any minimum tree. Jonah, you said, why did I go smallest to largest? That's the only reason. But I could do the reverse. What if instead of being weights or costs, these were rates? Here are the network connection speeds between these nodes in my network. Do you want the slowest network or the fastest network? Then you'd want a maximum spanning tree instead. Same algorithm works, just work high to low instead of low to high. So there is a really trivial change to go from minimum to maximum, and a real utility to it. We were having audio problems in this room on all of my recordings, right? I found out why. I thought it was because the wireless access point was way back there. there was a wireless access point right here in the podium. So that wasn't it. But I was plugged in right here to a 10100 line instead of to the gigabyte Ethernet. They plugged it into the wrong port, and it throttled my connection speed. I want a maximum speed connection. I can do that. All they did was unplug it and replug it in. And everything worked so far. Give me a minimum spanning tree here. Now, I apologize in advance. When I write it, I can't write build a MST. It just sounds wrong. But it's not an minimum spanning tree. So if you write out the word, it's a, but if you don't write out the word, you write the abbreviation, it's an. Twitch. And that gives you a weight of? Now read that to me again. A, B, B, C. That turns out to be a path. But that's a valid minimum spanning tree, right? Somebody get a different minimum spanning tree? Again, it depends on your choice of tiebreakers, right? I got a different minimum spanning tree. What's the weight of mine? $11. No matter what minimum spanning tree you choose, the minimum weight is the same. I should prove that this construction method results in a minimum spanning tree. Proof's about a page and a half long, and you prove it by contradiction. Suppose you didn't end up with a minimum spanning tree, then there must be an edge you can sub out and stay acyclic that will lower your total weight. Ad nauseum, okay, then I didn't have a minimum spanning tree to start with, there's my contradiction. It's annoying. I'm not going to do the proof. It's in the textbook. Read it. If you're interested in that sort of thing. But I would like to point out to you that the way in which we went about adding edges in the graph we built for this example jumped. We built AD. And then we jumped all the way over here to build CE. What was our very first example of a tree on Friday? That one, right? And it was roads. If you were building roads, you wanted to build the cheapest set of roads, now everybody can get to anybody else, right? That's my lowest cost set of connections. Would you build this road first, pack everything, and then go build this road? That's friggin' dumb, isn't it? Why? And then I have to move back because the edge we added after that was here. Really? So while Kruskal's algorithm adds edges without regard to where they are, Prim's algorithm builds edges same way by weight, but only by continuing to expand the tree you've already built. You stay connected at every step in Prim's algorithm. Don't in Kruskal's algorithm. So the fundamental difference between these two is not how we do the sorting or how we do the tie breaking. It's how we do the adding on. There are many different ways to write out Prim's algorithm. The version I have defines your graph as a set of vertices and then adds the edges in it. But you're only allowed to add edges that are connected to the one of the vertices you've already used. So, same graph, same empty set. Here. I need to start with a lowest weighted edge. Which edge do we start with? Okay. Now with Kruskal's, we would have jumped over here and built CE next. Prim says you must stay connected. Give me the lowest weight edge that is incident to either A or D. Say again, Cole? Great. Perfect. But you'll notice I'm only allowed to grab edges that are touching one of the vertices. Now, give me the lowest edge touching A or D or F. Aha, AB this time. Now, why is this better? Imagine your road building companies. You've just resurfaced or redone all these roads. Those are nice and easy to drive back and forth across. Well, now I've got 4 vertices, A, B, D, F. What's the lowest thing connected to any of them? Which also has a weight of, I've added a new edge. I've added a new vertex to my list of vertices I can work from. Next lowest edge connected to one of those vertices, which has a weight of 5. I knew it was going to come back at some point because it was the lowest weight edge I needed. It's got to be in there here somewhere. And now, the lowest weighted edge connected to any of these. Wait a second. Did we screw up our previous picture? What's our lowest weighted edge here? Say again? No, the next lowest weight edge we can add. I've got to get to G somehow, right? What's my lowest weighted edge to go to G? Well, I either go to G from E or F. Which one of those is cheaper? There you go. And that is the exact same picture we got before, isn't it? Does that always happen? No. It would be nice, but it's not a guarantee. And the answer is no, we didn't screw up our previous one. I just looked and read something wrong. Again, if I were being pedantic here, what I would say you should do is you should say, oh, first, I look at what vertex set is connected to my lowest weight edges. In this case, the edge AD, right? Now I can only look at edges that have an A or a D in it. 1, 2, 3, 4. There's a D. So what do? I add the one that is furthest to the left. I take out edges that are not incident to either of those, and I only look at the ones that are left. The one furthest to the left is the one I add. And now I say, oh, I have A, D, and F. Scratch out anything that doesn't have an A, a D, or an F. If I use AB, do I get a cycle? Nope, use it. And so on, right? And again, here's a complete write-out of the way this algorithm works. At every step, I'm looking at what candidates are available for me. Let's try that other version, that other graph. The other graph we had earlier was the squares with the diagonals, right? So, where's your starting edge? I'm going to be asinine and swap out my tiebreaker. Instead of picking the lowest letters, I'll pick the highest letters. So my tiebreaker for the edges of length 1 is BE. I pick this one. That's a weight of 1. Now I pick another weight 1 edge. It's either AB or AE. My tiebreaker says use the biggest letters. There's 1. What's adjacent to A or E or B with the lowest weight? Well, that's AB, but that makes a cycle. I can't use it. Next lowest weight is either BC or BC or EC. Highest letters would give me EC. Next lowest weight edge, adjacent to one of those 4 vertices. CF. I got to get to D because that's the only thing left. Do I use AD or ED? Based on my typebreaker algorithm, it says use the highest letters. There's my minimum spanning tree. Its weight is 11. That's different still, isn't it? Sorry? So alphabetical order. It was either A, D, or E, D. E is later in the alphabet. If you want to use the smallest alphabetical order, then you'd use AB first. And you'd use AD rather than ED. That's fine. It is completely and totally an arbitrary. We could literally flip coins every time we wanted to and make it completely random. I got dice with me today, people. We could do this. Teaching probability in the class right before you. I brought my dice. It works. A question for you. How would you code this? Blah. This is a very visual process, isn't it? That's a problem. Because if I have a very large graph, I don't want to do this by hand. I want to feed this sorting list into a computer, let it sort the edges, and then, there are 1,000 vertices in this graph. No, I don't want to do it. Got to be a better way. But to do so requires me to take this algorithm in particular and rearrange the way I describe a graph, which I absolutely cannot do in the 2 minutes remaining today, which means I will do it at our next class. But that's not Wednesday, because what's Wednesday? That's not Friday, because what's Friday? Because I will be elsewhere. So our next class, where we will finish this up, is a week from today. Don't let this leak out your brains over the weekend. I will see you all on Wednesday. Have a wonderful rest of your day. Yep.